on to the next set of questions. We have, there's quite a lot. Okay. So we have to use now to investigate basically the convergence of the improper integral. Right. So you integrate and then you check if the whatever you found within the limits of the integral, if the function does converge. So the first expression that we have is the integral of 1 over x times ln cubed of x. What should we use to solve this integral? Never mind the boundaries for now, because remember, you have to integrate first before you even apply those boundaries. So what should we use to solve this?
Use substitution.
Use substitution, okay? So what should we let our u be?
Our ln.
Okay, you can try that. If u is equal to ln, then du is just equal to 1 over x dx, right? So then, bringing it to the expression, you would have the integral of 1 over x multiplied by basically u cubed, right? And dx is just x du, right? So x du. So the x would cancel there. You have the integral from e to infinity of 1 over u cubed du, which is u to which is basically the integral of u to the negative 3 du, right, from e to infinity, and this is just u to the negative 2 over negative 2 plus c. And when you evaluate this, when you go back to the original u substitution, so you have now the integral of, or rather not the integral, but you have ln x to the negative 2 divided by minus 2, right, plus our constant of integration c, but now evaluated between e and infinity. And when it comes to those boundaries, you know that the constant will just fall away, right? So we don't have to worry about that. Now let's look at the upper limits. So if you substitute the upper limits there, which is infinity. So you have first ln of infinity, right? Obviously, this is positive infinity because you can only have the ln of a positive value. So ln of infinity to the negative 2 divided by negative 2 minus ln of e to the negative 2 divided by negative 2. Now, ln of e is 1. But now, what is ln of infinity?
Is it not 0?
Sorry?
Is it not infinity?
Yes. So when you go, when your x gets higher and higher, your ln gets to a very and higher value, right? So, and when you have that, remember that the exponent here is negative 2. So this can be simplified further to negative 1 over 2, basically, multiplied by ln of infinity squared. And ln of infinity squared is just infinity, so this would be 0. Right? 0. Minus, we said ln of e is 1, so 1 to the negative 2 is just 1. So minus 1 divided by minus 2, which would just be minus minus, so that would be plus 1 over 2. So the answer would be 1 over 2. Meaning that the integral does converge, and it converges to the value of 1 over 2.
So it's not necessary for us to add the limits and all.
What limits?
Because
What do
Mhlongo
you,
would
as
normally
in,
just change the infinity to maybe like E or A or something, just a variable. And then you have limit as infinity approaches, limit
oh,
as
yes,
B
okay,
or
yeah,
A
yeah.
approaches infinity.
You can do that as well. I mean, it's a style thing. It doesn't, well,
Oh, okay,
if he does
okay.
it that way, my advice is use his way because he's the one marking your your test. I'm not there.
But it's
So,
not necessary. I mean,
well,
well, in
well,
general.
yeah, but I mean, it doesn't change anything about your solution itself. You could just write
Okay.
it as like x tends to infinity of, -1 over
Oh,
2
yeah.
with
You're
x
correct.
squared. It doesn't change your actual solution, right? It's
Okay.
just a way to introduce the limits in there, but it doesn't really affect your actual solution. Your solution will still, well, this limit will still be equal to 0. That's my point. So yeah, maybe it's a nice way of him to show maybe that just to remind you of the limits, and maybe that it's the proper way, if you know what I mean. It's the proper way to write it, but
Okay.
it's the aesthetic way to write it, but there's no particular impact that I know of on your actual solution.
Okay.
But follow his way. I mean, you might lose a half a mark or something just for that, so you don't want that. So just follow his method, his way of writing stuff. He knows
Okay.
best. Right. So, any questions here? Any other questions? Okay, so let's move on to the next example, which is asking us to find the integral of 1 over x to the x minus 1 to the 1 over 3. Now, what I want you guys to do is guide me through this solution. So basically, you are solving this, and I want you guys to tell me what method should we use here.
So would you let okay, I don't know, introduce the limit still?
Limits? Why? Why? For what?
Because if you substitute one, okay, never mind, maybe I'm just like,
This is an integral, right? So
Mhlongo did something about discontinuities where like if you substitute that one in the denominator, you're gonna have 0.
but
So
you're
it
not,
breaks.
but that's not what you're doing now, is it?
Yes.
Okay, then. I hear.
Yeah, right now you're integrating first,
Okay, makes sense.
right? I guess, well, yeah, I guess
But
I think I kind of get what you mean, but
when should I think of that then?
no, okay, so just follow whatever example he gave you. So if he used it in a specific example and he explained it that way, just follow that, right?
Okay.
Yeah. So yeah. But anyway, so what you need to do, because this is a definite integral, it's still a definite integral. So what you need to do is you first need to integrate, right?
Yes.
That's the first step before you even substitute anything. So you integrate. So let's integrate. And
Let
what should we
you
use to integrate it?
let your u equal to x minus 1.
Yeah.
Right. Just give me a minute. Sorry if you don't mind. Just give me a minute. Mm. Mm. Okay, just give me a minute. Right, so the first step is your u substitution. So we let our u be equal to x minus 1. That was suggested. So then your du is equal to what? Is equal to dx, right? So then you bring it to the expression. You have the same integral from 1 to 9 of 1 over u, right, to the 1 over 3. And right, so then when you integrate this du, right, so then when you integrate this, you have basically the integral from 1 to 9 of u to the negative 1 over 3 du, which is equal to what? What is that integral equal to?
Three over 2.
Sorry?
3 over 2
Mm-hmm.
times u to the 2 over 3.
Times u to the 2 over 3. Okay. Evaluated between 1 and 9. So you have to go back first to the x before you substitute.
Yes.
So 3 over 2 multiplied by x minus 1 to the 2 over 3, evaluated between 1 and 9. And then you have the 3 over 2 can come out. The first is 9 minus 1, which is 8. So that would be 8 to the 2 over 3. Minus 1, which is 0. So that would be plus 0 there. 8 is 2 cubed, right? So 3 over 2 multiplied by 2 cubed to the 2 over 3. The 3 will cancel there, so you have 3 over 2 multiplied by 2 squared,
Sure.
which is equal to, if you simplify that, 3 times 2. Does it make sense?
Yes.
So the function does converge to the value of 6. Or at least that integral converges. Right. So I think maybe the reason why Dr. Mshlungu might have introduced limits here before he does any of this is to get rid of the case where x is equal to 1 in this function before you integrate. So that would be using a dummy, what is it called again? A dummy variable. I think that's so. As x tends to, let's say you use as a dummy variable a, that would be from well, not you could say, for example, you could use as a tends to 1, which is the problematic expression, the integral from a to 9 of 1 over x minus 1 to the 1 over 3 dx, just so you avoid the a being equal to 1 in the denominator before you do the integration. So I think that's the proper way to do it. But anyways, yeah. So just refer back to what he does and just use that. But the integration itself, so that's what I'm worried about right now. So the integration side itself stays the same, right?
Okay.
So any questions there? Anything else that you guys want to say?
Mshongo will be testing that those hyperbolic thingies, and we didn't really go through them. Even in the tutorials, he didn't have questions based on them. So I don't know.
Hyperbolic trigonometric expressions.
Yeah, integrals of hyperbolic functions. But he said it would just be like a simple one, I guess, where you use u substitution. Could you just do one example for us where you use U substitution, maybe for shek?
Okay. Right. So the integral of shek.
Yeah, but one that you can use U substitution, because you said you will use a U substitution to evaluate.
Wait. Let me see if I can come up with one. Just give me. Oh, one where you use your substitution. Okay, I think I have one. Yeah. Okay. I wasn't expecting to do this, but I guess we can do it. So, okay. Let's also try to solve the integral of this expression. Right. So then you guys know that sec of x is just equal to, it's equal to what? So if you remember from the first semester, sec of x is just equal to cos of x divided by cos squared. Well, wait, let me just rewrite it in a better way. So it's 1 over cos of x, which is the same as just cos x over cos squared of x, right? Makes sense?
Yes.
Right. So then, if you rewrite it like that, this expression becomes cos x over cos squared x dx. And you know also from your trigonometric expressions that, well, hyperbolic, that would be a hyperbolic expressions, but that cos squared of x is equal to something similar than the trigonometric ones. Sine squared of x plus 1, right? So this is equal to cos, integral of cos x divided by sine of x plus 1 dx. And now we can use U substitution here, right? So you can let, for example, our U be equal to sine of x, meaning that our du will be equal to cos x dx. And right, so our dx will be du over cos. And when you bring it to the expression, you have cos of x divided by our u squared plus 1, right? Multiplied by our dx, which is du over cos of x. Simplify that. You have the integral of du over u squared plus 1. And if you guys remember the example that we did in this same session, what is this integral equal to?
Arctan.
Yes, all right, so arctan of u. And you know that our u is sine, so we have arctan of sine. And that should be plus, obviously, the constant of integration. And that should be the final expression. Right, so that's just like a simple example on how this would work. But basically, just I guess for this type of questions, just go back to the identities. I think the only thing that might cause you problems is if you don't know these identities. But as you can see, they are quite similar to the trigonometric identities. But
So
there's some differences in terms of, for example, the derivatives and stuff. So go back to them and just well, not memorize, but sort of get acquainted with them so you don't get surprised in the test. Yeah.
so that's how they would like. I mean, that's how you evaluate the hyperbolic functions. Like you don't have. I don't know how to explain it, but you wouldn't have like, I mean, let's say numbers added to it, maybe like 5, 10, shek, x,
Yeah.
dx.
Obviously, you can. This is just a simple. For example, you could have 5 here, right? You could have x squared, right?
Okay,
-1. But well, basically, it's different variations, more
but they follow
complex.
the same thing.
Yeah, they would follow the same sort of logic behind. It's the same way we've been solving all the other expressions. It's just that it's a new set of identities that you sort of need to learn, right? For
Okay,
example, here in this case, as you can see here, the expression is different from the trigonometric one. The trigonometric one is cos squared is equal to 1 minus sine squared, right? Different. So there's some small differences there, here and there. But I guess the only thing that you can do is just practice with these and I'm sure your textbook has some examples as well using these types of expressions. So just refer back to that and also keep in mind the identities for those types. And maybe you can also ask him to provide some sort of revision or exercises that you guys should focus on for the tests, especially looking at these types of problems. Right. Um, any other questions?
you've covered most things that will be in the test that Mklongo had given us today.
Really?
Almost everything, in fact.
Okay.
Actually, everything. It's just not
Def-
the integration by parts.
yeah.
But you know,
So integration by parts, we've done it. I
we've
think
done.
quite
Yeah.
quite a lot before. So I think yeah, maybe to close off, I'll do this last one here, and then you guys can attempt this one as well, which is an interesting one.
Oh, actually, please, mate. I don't remember you telling us when we'd like complete the square, like things that will make us know that okay, we need to complete the square here. Also
Complete the
for like
square.
trig
Well,
substitution.
you would in okay. So how should I make this simple for you guys? In most of these examples,
Yes.
right? Uh, Especially for test two. This is sort of a general thing to say, so don't quote me on this. But I don't think you will have to. You'll need to go to complete the square in the
Okay.
questions that you'll find. In most cases, because you guys are dealing with trigonometric substitution, right? In
Yeah.
most cases, you will have you know either one of these cases, right? That you guys should be familiar with, right?
Yeah.
Right. Or you know, either one of these cases, right? And obviously, it could be the square roots, or it could be any other expression, for example, like 3/2 here that we have there. But like I think I mentioned on Saturday, it's usually they give you something
Over two.
like yeah over 2, yeah. So some number a over 2, because when you substitute in, and usually whatever is in there will be a square, right? So you can simplify easily
Okay.
by using substitution, by using your trigonometric expressions, because most of your trigonometric identities are in squared anyway. So it's sine squared equal to 1 minus cos, right? It's tan squared, equal to sec, right? most of these expressions are using squares anyway, so you know that most likely, okay, so don't quote me on this, but most likely you will have something like that.
Okay.
I don't think it would give you something too complicated, but then again, you never know. But I don't want you to. I'm not involved in it, so I don't know anything about what's going on there in the test. But you know,
You didn't mention it today.
yeah, hopefully, right. So plus, you guys also will most likely have a revision session. So just look at what you guys cover in the revision session. He's usually fair anyway, so right. Yeah, so for this one, we are dealing with the case where we have a squared minus sine squared to some constant, right? B over 2, right? So, and in that cases, in these types of cases, what do you think we should use as our U substitution, trigonometric substitution, right? So X. Sorry?
Sine.
Sine, yeah. So sine, and it would be sine of a sine of U. But in our case, a is 1, so we have sine of U. And because we have that, now we can apply it to the integral. Well, first we find dx, which should be cos u du. Applying it to the integral, we will have the same integral from 0 to half of 1 over 1 minus sine squared of u to the 3 over 2. Um, please mute yourselves so there's no background noise. Cos u du, right? So then this is equal to the integral from 0 to half of what? 1 over 1 minus cos squared is sine squared. Right, sorry. 1 minus sine is cos squared. So that would be cos squared u to the exponent of 3 over 2 multiplied by cos u du equal to the integral of from 0 to half of cos u du divided by cos squared to the 3 over 2 is just cos cubed, right?
Yes.
Cos cubed u du. You can simplify the cos there, and you have the integral from 0 to half of cos, du over cos squared of u du.
Hey, why do you have two D's?
Oh, sorry. This shouldn't be. Thank you. Right, so you have that. And then this is equal to the integral of 0 to half of
Sec.
sec squared, right? U du. And what is the integral of sec squared?
10.
10, right? So you have 10 u from 0 to half plus, well, not c, because we have definite integrals. So c falls away. So what's our u? Our u is sine inverse, right? Remember, sine inverse of x. So you have 10 of sine inverse of x. And where does the sine inverse come from? We know that x is equal to sine u, meaning that u is equal to sine inverse of x. Right? So since we have that, now we have to find a way to simplify this expression. And that's where our we manipulate our angles. So we know that if this is our angle, let's call it u, right? Because that's what we're dealing with. And sine, right? Sine of u is just the opposite side, which let's call it x, over the adjacent, right? Well, no, sorry, opposite over the opposite over the hypotenuse, right? So if this side is x, this side should have to be 1 minus x squared. The hypotenuse is therefore equal to 1. And therefore sine of u will have to be equal to x over 1, which is just x, right? Which is what we have here, right? That's our u substitution, that's our trigonometric substitution. But then that would mean that tan, right? So that would mean the tan now of the angle u, which is just sine inverse, right? Which is the same as tan of sine inverse of x is equal to what? Tan of u is opposite over adjacent. So x over the square root of 1 minus x squared. And there you go. So means that our integral is equal to x over the square root of 1 minus x squared evaluated between 0 and half, which is equal to half over the square root of 1 minus half squared, which is 1 minus 1 over 4, which is 3 over 4, minus basically 0, right? And you have half over the square root of 3 over 4 is just root 3 over 2, which is basically 1 over root 3, which is root 3 over 3. Good. And that should be the final answer there. Any questions? Any confusions about this part here? I'm sure you guys should probably remember your 131 last semester. I think it was one of the first tutorials where you were dealing with trigonometric expressions, where they were asking you to find cosine of sine inverse of something. I'm sure you guys remember that. So you should be familiar with these types of manipulations. But anyways, any questions there?
No.
Right, so moving on to the next expression, you have, I'll just set it up for you and then you guys will continue just for the sake of time because we are going way over time now. It's getting late. So here we have the case where we have a squared plus x squared. And in that case, you know that you have to let x be equal to what?
A tan theta.
Right, so a tan theta. And in our case, a is just 1, so x is equal to tan theta. So you have x is equal to tan theta. That means that dx is equal to sec squared theta d theta. So now you have everything to keep going. So try to move on. Have you guys had reduction formulas? Did you guys study reduction formulas?
What are actually reduction formulas? Because I feel like we have, I just don't know which ones they are.
Reduction formulas would be like, how do you find the integral? Remember, if you go, let's go back to the example. I'm not sure if I have it. So
like half 1 minus cos 2 theta.
No, this case here. So the reduction formulas would basically tell you how to solve this integral. Sine of to the 5t or sec to the 10t. So it's basically formulas that you use to quickly identify the
yes, they've taught us then. They've taught us.
Use those. Obviously, I think most of them are derived from integration by parts.
Oh.
I think, yeah. So just try to use both. try to use integration by parts. When you get to a question like that, try to use integration by parts when you're practicing, obviously. Don't do that in the test because you don't have time. So try to use integration by parts and try to use the reduction form.
Okay.
They should end up giving you the same thing.
Yeah.
But also, if I remember correctly,